That's the blooper reel. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the float lock vise today and I'm going to make the hand crank. And in fact, I'm going to try to make some improvements to the design that are in the drawings. So let's go. Here's the drawings for the crank. It consists of a base piece on the lead screw and then this separate crank piece here that's hinged to it. I'll pause here and point out that I'm going to make a change to this part. The drawing shows a static handle. It's all one piece. And I find static handles quite annoying on hand cranks because you have to let it slide through your fingers as you crank, and it's difficult to crank quickly, and it's almost impossible to crank if you're wearing any kind of gloves where the handle won't slide through your fingers. And this is important on this particular float lock vise because it's actually quite a fine pitch lead screw for a vise. These drawings were made from the original junior model of the float lock vise, but on the later upgraded models, they had a quick travel mechanism. It was a ratcheting device rather than just the basic lead screw that the junior model has. And this would alleviate the tedious cranking problem of the junior. I think they went with this fine pitch lead screw because the crank is quite small on this vise, and it's necessarily small because of the limited space you have on the drill press table here. Big vices have coarse pitch lead screws for speed, but they have room for as big a crank handle on there as you need. Lead screw pitch is always a compromise between jaw speed and clamping force, so I think the fine pitch on the float lock gives you sufficient clamping force with a very small crank. So I'm going to put a speed handle on this, which is just a sleeve that goes over it that's captive like you would find on a milling machine, and that'll make this a lot more pleasant to crank, I think. So I've got this piece of cold rolled steel here that I'm going to use for this crank, and I'll start with that base piece there. Now the nominal OD of this is basically right on what the finished part is supposed to be, but I'm going to use it anyway because it's nice material and the finish on this crank doesn't have to be perfect. I'll get this chucked up in the lathe and face the end, as is tradition. This end is going to be the reference for many of the subsequent features, so it's an important surface. And I'm going to start by making the hemispherical end of the hinge piece. For that, I'm going to use the hinge cross hole as the reference, so I'm going to set it up here in my cross drilling fixture. This fixture allows me to edge find on the fixture itself. It's designed to be used this way, which makes it easier for round stock, which is sometimes tricky to edge find on. And then that recently created reference surface will allow me to find the end, and I can translate into where the cross hole belongs. That end face there will become the tip of the hemisphere eventually, but for now it's going to locate this hole. I started with the center drill because we're on a convex surface here, which would cause the drill to wander off if we didn't. And then I pilot drilled and reamed this to size. There will be a pin in here eventually, so a nice reamed hole will be good for that. Now back to the lathe and I can create the hemisphere. Concentricity is important here because the hemisphere is going to be aligned with the OD of the stock that won't be machined. So you might think I'm crazy for doing this in the 3-jaw, but you can actually find a jaw position where the concentricity is sufficiently good enough. And in this case, I got really lucky and found it on the first try. Just to keep my integrity intact, here's 2 other jaw positions on this same stock and same chuck where it's not nearly that good. So this is more typical. So I got very lucky on that first attempt. To create the actual hemisphere, I'm using the step turning and filing technique that I demonstrated in a recent video. If you want to know more about this process, go ahead and watch that other video, which I will link to below. I don't want to go into the entire process here, but there's a technique here for using the file that guarantees accurate results. As you can see here with the radius gauge, we're basically right on there. Certainly good enough for a hinge feature. I had the stock choked up there to make the hemisphere feature since there was a parting blade involved, but now I want to pull it out to create some other features here. Now normally you don't want to move stock in a 3-jaw or you lose concentricity, but you can get away with it sometimes if you're careful not to rotate the stock as you pull it out. It's usually still going to be close enough if the stock is good quality. I measured a little bit extra long and I'm going to part it off here. And unfortunately my parting blade was all choked up for the step turning operation. It's part of how that process works, and so it wasn't long enough to part all the way through the stock, and I didn't want to adjust it because then you have to set the center height again, and just finished with the hacksaw. Yahtzee! Now I can flip it around and do the features on the other end. So I've parted it off long, and now I'm facing it down to final dimension here. If this were a critical part, of course, you also would not want to flip it in a 3-jaw like that because you're going to lose concentricity. But again, this is a simple hand crank, and this is all just fine. Now the one critical dimension here, though, is the depth of this hole, because it gets very close to a feature on the other end that we'll be making later. The drawing is not super friendly in this way. So I've got the feeler gauge out, and I'm using that to make sure I get the drill exactly on the surface of that so that I can put an indicator on my quill and measure the exact depth that I'm traveling, plus the thickness of the feeler gauge. This method works really well for getting very precise drill depths. We can't go too deep there or we'll mess up a feature at the other end, but if we go too shallow, then the crank won't sit in the correct place. So I'll double check that now. I should have enough depth there to where the lead screw goes all the way in against the jaw there, but there's still a little bit of end float there, and we have that, so looking good. Back over to my cross drilling fixture now, and I'm going to drill the other cross hole that this part needs to attach it to the lead screw. I guess I could have done both of these in the same setup earlier, but oh well, here we are. Now before I go any further, I want to do a little test fit here with the assembly and make sure everything's going to go together properly. So that is looking good. Those holes line up for that pin, and we've got just a little bit of end float on that so that it'll spin freely. That's just what I want. In hindsight, it would have been a lot easier just to assemble these parts and drill them both through at the same time, but I'd already made the cross hole in the lead screw, not thinking ahead far enough. I did make one little boo-boo though. The first cross hole that I drilled was too small. I confused the 125 and the 156 holes, so I got to set it up here again and open this up. So here's a quick and dirty way to get back aligned on that feature. I've got a gauge pin through the hole there on the spindle, then I line it up with the collet block while holding it vertical, then I release it from the pin and slide it into the collet block, and then verify that the pin is still aligned vertically there. If you try to do all of that at once, it's too many constraints and you'll just end up bending the gauge pin. But if you line up one constraint at a time and do it carefully, then that does work. And then I can open that hole up to the proper size. That was not a waste of time though, because I needed the part aligned in a collet block anyway so that I can stand it up vertically like this, and that cross hole reference there is going to be X aligned on the mill once I set it up like this. And to get it sufficiently vertical, I'm just using a square and a light here. If it was more critical, you would want to indicate in that block, but the light will get us there. Now I need to align that hemisphere on the spindle, which you could do with a DTI or a coaxial indicator, but we can get sufficient accuracy here just by putting in a collet of the correct size and very lightly seating it on the taper, and then just fiddling with the table until that collet slides down over the part. If the part is the same size as a collet, this works just fine and gets you within a couple thousandths of concentric. Now I can mill the slot feature in this part that's going to become half of the hinge. This is my nemesis feature, a deep square-bottomed slot. I never like these in drawings. Don't put these in your designs. Just allow extra room for a round bottom slot, and then you can mill it horizontally, which is always a lot easier. Because, for example, in this case, I had to use a special long reach end mill, and because it's long reach and it's small in diameter, it's not rigid, so I had to do a lot of light cuts to get this feature done. But there's another catch with this feature that I'll get to in a minute. Onto the other half of the hinge now. I've put the hemisphere on it and the cross hole in the same way, and I measured the width of my grooving tool and then lined it up on the edge of the sphere there, because that's the reference on the drawing for this next dimension. And then I can move down and put a groove in here to establish a shoulder here. Here's where my modifications start for the speed handle. So you'll see what I'm doing here in a minute. That shoulder that I've established is going to be eventually the final dimension of a much more slender shaft than is in the drawing. So I want to taper that down to the larger head there on the end of the hinge. So I set my compound over to 45 and I tried to cut this taper thusly. Unfortunately, the only left-hand tool I have was much too large for this, and I just couldn't get the clearance in there to do it. So I switched over to the chamfering tool to see if I can get away with this. It would be a very, very large chamfer in steel, which usually you can't get away with in a small lathe like this. But I ran the lathe very, very slowly and took a very light cut, and I did manage to get it done. This is also free cutting steel, so that helps a lot. Unfortunately, this was going so well that I didn't notice I went too deep and put a little ring there in the middle of the shaft that I did not intend. Let's just call that a decorative touch. There are no mistakes in machining, only unscheduled Art Deco details. With all the features established at that end, it's now safe to mark it for length and part it off so I can flip it over. I've got a bunch of turning in the middle there that's going to require tail support, but I can't put a center in the end of my nice hemisphere there, so I'm going to flip it around and do that stuff from the other end. So in with the parting blade, and Yahtzee. For once I did think through this order of operations a little bit, and I've got enough meat there to hold with the 3-jaw, and I can very lightly face off the end. This is the very definition of an unrigid structure here. A lot of stick out with a neck cut down right at the critical moment there, but it was sturdy enough to take a light facing cut, and then I could put a center in it and finish turning down the skinny part of the shaft here. Now again, this is where the drawing calls for kind of a barbell shape, because there'd be a skinny shaft in the middle with a thick section at the end for the actual handle, but I'm not doing that because I'm going to do a speed handle instead, so I'm turning the entire thing down to a much smaller dimension. And then I'm going to drill the end and tap for a screw that's going to hold the speed handle in place. Once again, of course, deviating from the drawing here, but if you look at the handle on a milling machine or the cross slide on your lathe, it probably looks very much like what I'm doing here. So in we go with the spring-loaded tap follower, and I'll tap that. I just ran that thread in about an inch or so, doesn't really matter. And I'll just break that corner while I'm here as well. And that's it for the lathe operations on this part. Looking good. Back over to the mill now, and I have to set it up in a collet block once again, and I'm using that trick to align that hole with the collet block and the spindle. And this is the tab that goes with the slot feature that we just created. So touch off on the top, and I need to touch off on the end because the drawing specifies the depth of the slot from the end of the sphere feature, not from, for example, the bore in the center, which is probably how I would have done it. It's a bit of an interesting choice that is going to create some interesting issues here in a moment, so stay tuned. But thanks to the collet block, I can just flip it over and line it up with the edge of the vise again and machine it down to the same value on the quill DRO, and we're going to end up with a perfectly centered and well-aligned tab. Collet blocks are awesome. Now I can do a test fit with the 2 hinge pieces, and let's just see how that goes. So I've got a nice fit on the tab and slot there, and I'll put a temporary pin through the holes there, and nope, they don't line up. So I fiddled around with this a little bit, and I determined that the tab is actually bottoming out in the slot. So this slot is too shallow. How did that happen? Well, let's go look at the drawing because this is actually pretty interesting. The tab is dimensioned at 626, which makes perfect sense. It's the radius of the curve plus a little bit of margin for travel. But the slot is dimensioned at 610, which seems like an error, right? Well, it's not, because it's dimensioned from the edge that will exist after you cut the slot, because we're milling away the top of the hemisphere. And as you saw, I touched off on the top of the hemisphere and then milled down 610. So that's why the slot ended up shallow. So it's a weird choice on this drawing that they referenced the dimension from a feature that doesn't exist yet until you create the feature. That'll throw you. You gotta watch things like that sometimes. So if it were me, I would have referenced that slot from the other end of the part or from the bore, something constant. Curved features are dangerous things to use as references, especially if those curves are gonna get modified along the way. Something to think about when making your own drawings. On further inspection, I think this is just an error in the drawing. The draftsperson didn't intend to use that edge as the reference. It probably got selected in SolidWorks by mistake or something, because elsewhere in the drawing it shows the 5/8 dimension there. So something to be aware of if you're using the drawings that are publicly shared for this project and are linked below. Luckily the fix was easy. I just set it up vertically again and deepened that slot another 20 thou. And now the pieces go together beautifully, and I've got an excellent hinging action there. So this turned out great. Luckily the error was in a forgiving direction. Now it's time to bend that shaft 90 degrees to form a crank, and I thought, hey, this is a great opportunity to try a model engineering technique that I've seen in the books. You drill a hole the same size as the thing you want to bend, and you file a radius in that hole, and that way the shaft will bend into a nice controlled radius. So I clamped the part up in the vise, slid the bending form on there, and proceeded to heat up the spot where I want the bend to be with the acetylene. Now, you probably see where this is going. I did not, but you're about to witness what might be the stupidest thing I've done in at least 20 minutes, maybe even 45. Yeah, 45 minutes. The bend went super well. Got the part nice and hot there, right where I wanted it. The bend actually went outboard of where my filed radius was, so that didn't work very well. And aluminum was not a good choice for this because it melted the aluminum. But, well, this was the moment where I realized I can no longer remove that block. Well, that's the blooper reel. Go ahead, you can laugh. It's pretty funny. This is a pretty stupid thing that I just did. So then I got to spend an hour trying to figure out how to free this thing from its aluminum prison. I ended up throwing a roughing end mill in there. Because it's just aluminum, I can mill it out very, very aggressively, even with my small mill. So I milled down as close as I dare to the steel. I didn't want to damage it, and tried to free it with careful application of a cold chisel, but I couldn't quite get enough material clear to free it this way, so I put it back in the mill, 90 degrees, milled out a bunch from another side, and that was finally enough to where I could free it from its aluminum bondage. Well, that was an adventure, and the part looks a frightful mess now, but a little trip to the Scotch-Brite wheel, and it's factory fresh once again. But despite that embarrassing side quest, the bend went really well, and it's right where I wanted it, and it's a good length, and I got the angle right, so we're ready to go ahead and make the speed handle. I've got a nice chunk of brass here that I'll cut to length here, and we'll throw it in the lathe and face off the end as is tradition. I want to do a tapered handle here because it'll look nice, and tapered handles feel nice in the hand. So I'm going to turn the stock down to the diameter of the big end of the taper, which arbitrarily I chose as the same diameter as the original handle in the drawing. Then I did the math for the length of the handle to figure out what a good taper would be, came out to 10 degrees, swung my compound over to 10 degrees, and proceeded to do this cut. I just did it in a single pass all the way down the length of the taper because it's just brass, which cuts very, very easily. The cut went super well. But right around here is where I thought, you know, that taper doesn't look right. That seems aggressive. And boy, was it ever. I didn't even get to all the way to the end, and it was clear that is definitely too steep of an angle. And this is where I remembered that, oh yeah, the compound on my lathe shows included angle, not the half angle. So I had to set it to 5 degrees to get the angle that I wanted. I made a lovely scale model of a traffic cone first as practice, and then made the final crank handle as you see here. Next I need the hole down the center to fit over the handle, so that's a simple center drill and drill operation. For an approximate depth like this, I just measure and mark directly on the drill with Sharpie, works just fine. But you can see I've got a mark there, and a mark there, and there's one there, and there's one back there, and you might ask, how do I know which mark is the right one for this operation? And the answer is easy. It's the newest one. This is drilling very nicely, which usually means the drill is a little bit dull. Brass actually wants a 0 top rake on all cutting tools, including drills, so a blunt drill works a lot better than a sharp one. The sharp ones get pretty grabby. So when brass is drilling really nicely, it might be a sign to sharpen that drill. I need a large, shallow counterbore in the top of that for the screw head that retains it. I'm going to bring in my Morse taper end mill holder. You can chuck end mills directly in Jacob's chucks. People do it. I don't like to do it. You're really not supposed to. End mills are very hard, as are Jacob's chuck jaws, so they don't grip properly. It's not great for the chuck, but for a light cut like this, it's probably fine. So I'll go ahead and plunge this 2-flute end mill into a reasonably accurate depth based on the quill markings. Not a lot of precision required here. And I've got a lovely little counterbore just like that. While I'm here, I will file a fillet on the top edge of this because it's going to make it more comfortable to hold in the hand. And that looks and feels very nice. That should be a good handle. I'll measure the length just with the scale here to part it off. Once again, this is all low precision parts here, plenty of wiggle room on everything. In fact, things being a little bit sloppy on length and diameter is actually helpful because it'll make the handle run smoother. I've got enough material here left for the screw that's going to hold it all together, so I'll face off the detritus from the previous operations. I need to get very close to the chuck here, so here's a little tip. Put the scale on the edge of the tool holder and bring it in to where it's not quite touching that jaw. Then you know when you feed in with that tool, the tool holder is not going to hit the jaw because there was room for the scale there. So I'll put a little witness mark there. That's kind of my safety line, and I can turn down the OD to just short of that line, and I know I'm not ever going to hit the chuck jaw at any point in this turning. I'm going to turn down to the OD of the head of the screw. And I'm not measuring anything here. I'm just going to work from the top down, and that's just going to make sure everything works out here. This is just a very freestyle kind of operation. So I'm starting with the parting blade, counterintuitively, and that's going to establish the top of the face of the head of the screw, and then I can work down from there and know that I'm going to have enough material. I measure the thickness of the head with the scale, and then I plunge in here again a little ways to establish the shoulder. Not to final dimension, just in a ways sufficient to have a clear shoulder there. And then I can turn down the threaded area to meet that shoulder. So by starting at the head of the screw and working down, any error that accumulates is just going to get pushed out into the area that doesn't matter, and I don't have to measure anything. The only dimension that's critical is the diameter here so that the threading goes well. This is a coarse thread in brass, which can be tricky to start because the brass isn't really strong enough to pull the die through based on a single thread alone. So what tends to happen is the die just chews up the end of the part over and over, and it doesn't ever catch. So I put a lot of pressure on it to start, and then once I've got a couple of teeth engaged on the die, then it'll pull itself down. These days I like to file a fillet on the end of a screw like this instead of just a plain old chamfer. I find it looks nicer and makes the screw nice and easy to start. And now I can come in and finish with the parting that started this all. Of course, if you have a DRO, you could mark this tool position and get back to exactly where you were, but you can also just do it by feel. And Yahtzee. I need a screwdriver slot in this screw now, so here's how I'm doing that. I've got it set up in my little toolmaker's vise because it's got a nice V-groove in the jaws for holding small parts like this. And I'm bringing the slitting saw down very slowly, cranking the column, not the quill. You'll see why here in a moment. Until I just feel those teeth start to skim the top of that. Then I zero the Z-axis on the DRO there, pull it clear, and do the same process on the bottom of the head, pulling it up very slowly until the teeth just skate on the bottom. The reason I do that with the column and not the quill is that the column allows me to use the half function on the DRO for the Z. I don't have that on the quill DRO. And that's a very easy way to get exactly on the center line and not have to calculate the thickness of the saw or do any kind of math like that. Any kind of errors in your setup, or no matter how thick the saw is, just using that half function is going to guarantee the feature is on center line by doing it that way. I'm cutting it on the back of the vise because I don't have the Y travel to do it on the front of this setup, so you're actually getting a better view than I am. And there's my little bespoke machine screw. You could polish it up if you want, but this tool is going to work for a living, so I'm not too worried about that. There's the speed handle, which you saw earlier, so that slides over like that. Gives a little bit of clearance in there so the handle has some end play in it. It's important for it to be able to slide in and out a little bit to move freely. And then I'll just crank that in there. Now this is a dissimilar metal, a brass screw in the steel handle, and I chose the brass because it looks nice, but I'll put a little anti-seize on that as well because of the dissimilar metals. But that looks pretty good. It spins extremely freely, which was the goal, so that should be a sufficiently speedy speed handle. Now I can assemble the hinge pieces here. I'm going to use a roll pin for this. I considered using a smooth pin, which would make the hinge very free-floating and floppy, but the handle on my current drill press vise is very floppy, but it's annoying because it rattles when the machine is running. So I wanted this hinge to be snug, but still, of course, you have to be able to move it. And I think a roll pin is going to achieve that. The two parts have oil on them already, but I added a little bit more down there just to be sure. And then I kind of worked that hinge back and forth to make sure that it's loosened up a little bit. and that actually worked really well. The roll pin made a snug hinge, but you can still easily bend it to any position, and then it'll stay wherever you put it. And that will definitely not rattle when the machine is running, which is good for my mental health. Quick test fit here on the lead screw now. I don't want to pin this permanently yet. We're not ready for final assembly there, so I'll just temporarily pin that in place and make sure that it functions as a crank. So there you go. That in fact functions extremely well. That speed handle was, I think, a good upgrade. I think I'm going to be really happy with that. I really love speed handles on cranks. And I like that the crank can be easily bent to any position and it'll stay where you put it. Well, there's my final little crank. I'm pleased with how it turned out, including the definitely intentional Art Deco detailing that I strategically applied there. A few little adventures along the way, but the part came out great, I think, and it's certainly going to serve as a functional crank for this float lock vise. Well, thank you very much for watching. I hope you enjoyed this little adventure, and I will be finishing up this vise pretty soon, so stay tuned. Check out that playlist in my playlists. Thanks to my patrons who make all of this possible, and I'll see you next time.